Hello, Year 10. This is Dr. Beck with another triple science chemistry presentation. Today we are going to continue looking at moles, and today we're going to focus on this part of the curriculum you can see here. We are going to be able to balance an equation given the masses of reactants and products. Okay, so our focus today is going to be on that. As always, in your book, could you please write down today's title, today's date, and today's learning objective? Take a minute to do that, pause the video, and come back when you're ready. Okay, so today's chemistry lesson is going to be based upon reacting masses and balanced equations. We're going to learn today how to use masses of reactants and products to balance chemical equations. Before we begin, as always, I'd like to give you a little starter task, perhaps a little bit complex, but hopefully you should all be able to do at least some of it. I'm showing you the task on screen now. There is help available, the top right. Answer as many questions as you possibly can in your book. The questions are shown on the screen. Give yourself no more than 5 minutes. If you're struggling, don't panic. Have a go, but if you're struggling, we will share the answers. So pause the video and come back when you're ready. Okay, so we have this equation. It is not balanced. Hopefully you can see why. To balance it, we need to add those little numbers. Could you please have your purple pens ready? And we will go through this starter task. First of all, we need to add the number 2 in front of HCl, hydrogen chloride. If you've got that right, give yourself a tick. What does this tell us? One molecule or mole of hydrogen reacts with one molecule or mole of chlorine to produce 2 molecules or moles of hydrogen chloride. And again, we know there's a reaction because there's an arrow. We have our reactants on the left, we have our products on the right. This is what this equation tells us. The relative formula masses, well, I gave you the atomic masses of the atoms involved. For hydrogen, it's simply 2. For chlorine, it's 71. For hydrogen chloride, 36.5. Well done if you got those right. And then for our extension challenge, how much hydrogen chloride would you produce if you reacted 4 grams of hydrogen with chlorine? Well, if you put those molar quantities in there, we end up with simply 2 grams reacting with 71 grams to produce 73 grams. Remember, we're having to scale up HCl, 36.5. We're going to multiply that by 2 because there are 2 molecules there. The question was about 4 grams. So even if you haven't answered that already, look at that equation now. How do we get that answer? Well done if you said 4 grams produces 146 grams of hydrogen chloride. Okay, so if we're at this stage where we're getting everything right, that's working at a really good level for our GCSE chemistry. We're looking at least a grade 6 or 7, and obviously today we want to extend that further. If we're confident and growing in confidence, we're in a good position going forward. Okay, today then we are going to be looking at balancing chemical equations. Now we know how to balance chemical equations. We're going to use a slightly different method to do it. We're going to be looking at the masses of each thing. So what I'd like you to do is just take a minute, please, to write down for this lesson the key words for this particular video. Pause it. When you've written the keywords down, come back and we'll move on. Okay, excellent. So today we're going to use the masses of the reactants and products to balance chemical equations. At this point of the video, I'm not going to click on this link, but I will post the presentation on Show My Homework. And there is a nice link through to an online video on YouTube that somebody else has made. I don't want to show it here. But in your own time, have a look and refresh your memory about reacting masses. The link will be sent with the homework. Okay. Now, chemical equations are incredibly useful. The reason they're incredibly useful is if you're a chemist, if you're a scientist and you want to make a certain quantity, you can use it to help you to not waste things or not produce too little. Chemical equations can be used to predict the amount of chemicals needed and the amount of chemicals produced. This ensures that chemical reactions are safe and as safe as possible and don't produce lots and lots of waste. Waste which can damage the environment, waste which is simply a waste of money. Okay, so we need to get this idea of it's not just stuff on paper we're doing to answer exam questions. The principle is that it's very, very useful and we can use it to help us produce the right amount of our particular product that we need. We are going to today be using the idea of moles to balance equations. And again, this is the second video. I'm not going to show it to you now. There will be a link in the presentation to a video online that I have not made. It's somebody else's. So please follow the link to help you with this next part. We're going to use a worked example. How can we use moles to balance equations? For a particular reaction, we can work out exactly what's going on and then balance chemical equations just from taking careful measurements. Okay, so we can produce our balanced chemical equations just by taking careful measurements. For example, the chemical sodium nitrate, NaNO3, decomposes when heated to give sodium nitrite, NaNO2, and oxygen gas. Okay, now this is a typical kind of question. You've got the words, the chemical names, but you've also always will be given the molecule formula, the chemical formula for the molecule. Now some of you may be way ahead of me right now, and some of you might have figured out, actually I can balance this really easily. Okay, maybe you can, and well done if you can, but that's not the purpose of today's lesson. We're going to go through how we can balance it from measurements of amounts, measurements of masses of our products and reactants. And here we have a particular example, which we're going to work through. When 8.5 grams of sodium nitrate is heated until the reaction is finished, 6.9 grams, that should say grams, apologies, of sodium nitrite is produced. 6.9 grams of sodium nitrite produced. There's two parts to this question. First of all, how much oxygen has been made? And secondly, what's the full balanced chemical equation for this reaction? Now, this is actually a question I've taken from the textbook. So we're going to look at that right now using the textbook. So here's the same thing taken from the textbook. Notice top right, always for these things, make sure you have a calculator ready. So if you haven't got a calculator, please make sure you pause the video, go and get one, and resume when you're ready. Okay, sodium nitrate, NaNO3, decomposes on heating to give sodium nitrite, NaNO2, and oxygen gas, which is O2. When 8.5 grams of sodium nitrate is heated until its mass is constant, 6.9 grams of sodium nitrite is produced. What mass of oxygen must have been given off? And find the ratio of reactants and products, and then how these can be used to produce the balanced symbol equation. Now, for this one, we don't need our periodic table because you're giving all the information you need, but it's always handy to have it with you. Once again, if you don't have one, go and get one, come back when you're ready. All right, let's have a look at part A. That's probably the easiest bit. We must remember about the conservation of mass. We know for any chemical reaction, the total mass of reactants equals the total mass of products. So if we're going to use the law of conservation of mass, we're just going to say for now that whatever the mass of oxygen is, we're going to call it X grams. So have a look at this. This is our equation, and these are the grams the masses involved, how much oxygen will be produced. Write down the word equation, write down the masses, and fill in and replace the X. What is the mass of oxygen produced? 30 seconds to do that. Come back when you're ready. Okay, so this is a thing that often confuses students. They're thinking, oh, well, in my calculator, I need to do some weird calculation. No, it's simply adding two things together, or in this case, doing subtraction to get our desired answer. So simply, it's 8.5, take away 6.9. The missing mass must be oxygen. So nice and simple, we should get 1.6 grams as the mass of oxygen produced. Well done if you got that right. So now we've got the three masses. We can now move on. From the masses given in the question and our answer to part A, you can now work out the number of moles of each reactant. Now for the number of moles, we need two things. We need the mass and we need the relative formula mass. First of all, you'll need to calculate the relative formula masses, the MR, of the reactants and products using the values that you were provided with. So if we follow that through, we find that the relative formula mass of sodium nitrate is 85, of sodium nitrite is 69, and of oxygen is 32. The relative formula masses of each of those molecules. Next, then we can use our equation from our previous topic to convert masses into moles. So the mass in grams of each one divided by the relative formula mass of each one. So we have 8.5 grams divided by 85, the relative formula mass for sodium nitrate. 6.9 grams divided by 69 for sodium nitrite, and 1.6 grams divided by 32, the relative formula mass of a molecule of oxygen. When we do those calculations, we come up with these moles, these number of moles. For sodium nitrate, it's 0.1. For sodium nitrite, it's also 0.1. And for oxygen, it's 0.05. What's the next step? We're going to find the simplest whole number ratio. Now, these are the ratios we've discovered. They're not whole numbers. We're going to find the simplest whole number ratio of the numbers of moles of these three different molecules. So we've already worked out that the numbers of moles for the three things are in this ratio, 0.1, 0.1, 0.05. We're going to divide by the smallest number. Okay, so 0.1 is divided by 0.05 is simply 2. 0.1 divided by 0.05 for the second one is also clearly 2. And then clearly for the last one, 0.05 divided by itself gives us 1. So we have a whole number ratio, 2 to 2 to 1. And this we can then add to our chemical equation. The number of moles required of sodium nitrate is 2. The number of moles required of sodium nitrite is also 2. And the number of moles of oxygen is 1. As always, if we don't need the 1, leaving it blank and just leaving no number in front of O2 is absolutely fine. So our balanced chemical equation is this: 2NaNO3 reacting to produce 2NaNO2 plus O2. Now, again, you've probably worked that out well before, and I could probably give you that without the large numbers, and you could work it out in a matter of seconds. But we need also to know this method, okay, using the reacting masses to working out a balanced chemical equation. What are the steps then? Again, as I go through these, if at any time you want to write these down and pause the video as we're going, please do that. The first step is to write an unbalanced symbol equation. work out the molecular mass, the formula mass, or the atomic mass of everything in the equation. Work out the number of moles of everything you have using mass divided by mR or AR. Convert to the whole number ratio by dividing by the smallest mass. And then put these numbers into the equation, and that will give you the correctly balanced symbol equation. Again, if you want to write that down, please pause the video and come back when you're ready. Okay, we're going to go through in a second another example. I'm going to show you on the whiteboard how to do this. So today we're learning how we can use masses of reactants and products to balance chemical equations. And here is our key point. You can deduce balanced symbol equations from the masses and hence the ratio of the number of moles of substances involved in a chemical reaction. We're going to use a shared example, and here is a past paper question. We have the question that copper reacts with oxygen to form copper oxide, CuO. Just realized there's a mistake there. Apologies for that. CuO. In an experiment, 6.35 grams of copper reacts with 1.60 grams of oxygen. Balance an equation for the reaction. Now, hopefully you've spotted that this should not be here. Apologies for that. It's simply the relative atomic mass of O, oxygen, the atom. So here we go. The AR of Cu is 63.5. The AR of oxygen is 16. How do we go about balancing this equation? Well, first of all, our first step is to write down the unbalanced chemical equation. So here we go. Cu plus O2 is reacting to produce CuO. You're given the formula for copper oxide, and we know the rest. Again, we could actually balance that ourselves, but again, that's not the point of this exercise. We need to use our reacting masses of these. Okay. Now, first of all, we are going to work out or write down either the atomic mass or the relative formula mass. For this, we are already told it's 63.5. For this, we have 16 times 2 equals 32. And for this one, we simply have 63.5 plus 16, which gives us 79.5 for copper oxide. Okay, let's go back to the question. 6.35 grams is going to react of copper is going to react with 1.60 grams of oxygen. Okay, so let's write that down. So the masses that we have, 6.35 grams, 1.6 grams. So how much of copper oxide is going to be made? Shout it out. Good. Hopefully you've all shouted out 7.95 grams. That's our law of conservation of mass. The next step is to begin to work out our ratio. We divide the mass by the relative atomic or relative formula mass. The numbers here are nice and simple. That's good. This is often what's going to happen in an exam paper. 6.35 divided by 63.5 gives us 0.1. 1.6 divided by 32 gives us 0.05. 7.95 divided by 79.5, 0.1. We're going to divide each of those. Those are not whole numbers, clearly. So we're going to divide those by the lowest number. The lowest number here is 0.05. So 0.1 divided by 0.05. 0.05 divided by 0.05. 0.1 divided by 0.05. Put that into our calculator. Do that now, please. Okay, good. We have a whole number ratio of 2 to 1 to 2. Now we must go back up to the top, 2 to 1 to 2 in that order. So that tells us we must have 2 atoms of copper reacting with oxygen to produce 2 molecules of copper oxide. Now, as a final check, you can check for yourself, knowing your knowledge of how to balance equations, whether or not that is the correct answer. And to me, that looks absolutely fine. So we've done really well there, following it through step by step, using our steps in our method. Okay, apologies for the mistake on the board. So again, step by step, write an unbalanced symbol equation, work out the MR or the AR of everything we're going to be looking at. You need to do every single thing. We're going to work out any missing masses, work out the number of moles that we have of everything using our equation, convert to a whole number ratio divided by the smallest number for each case, and put those numbers back in the correct order back into that equation. If we do this for each time, we won't go wrong. Okay, for our homework for next week, in our booklet we have these 2 questions, questions 38 and 39. I would like you for your homework before next week to complete question 38. And if you finish that and you're feeling really confident about that, then have a go please at question 39. We will check the answers when we meet again in our next video. Okay, so today then we've been learning how we can use the masses of reactants and products to balance chemical equations, and we found out that we can deduce the balance symbol equations from the masses of substances involved in a chemical reaction. And we do that by calculating the ratio of the numbers of moles, and that ultimately will give us our balanced chemical equation. Okay, hopefully you found the video useful. Any questions, please email me as usual. For now though, have a good rest of the week and make sure you are completing your homework in time for our next lesson. See you next time.